Today we're going to be discussing enantiomers. If you see the pause sign in the lower corner of a slide, that means I expect you to pause the slide long enough to copy down whatever's on there into your notes. It's important stuff. I promise not to use it unless it's really needed. We built some enantiomers in the last class. We based them on a chiral carbon, a carbon that had 4 branches that were each unique. And that allowed us to build a structure that had a mirror image that was not a duplicate. These 2 mirror image molecules can be separated by their ability to polarize light at 90-degree angles from each other, which means they can be separated fairly simply from each other within the lab. So yeah, we can tell them apart, but why would we go through the trouble? Well, just like your right hand fits into right-handed glove, some molecules only fit if their shapes are right. If it happens to be their mirror image, that molecule doesn't function the same way. This happens a lot in biological molecules, which tend to be carbon-based and have a lot of carbons, so the possibility for a chiral carbon increases. Some common examples: starch versus cellulose. They're enantiomers of each other. The enzyme that allows you to digest potatoes or bread doesn't allow you to digest wood pulp the way a termite's enzymes can. Those two are enantiomers of each other, and just like a mirror image of a key wouldn't fit the same lock, the same is true with these enzymes. Adrenaline, 20 times more potent in one of its forms than in its enantiomer. Carvone is another one. It's a chemical that gives a fragrance to dill, the spice. And the enantiomer of that is spearmint, or at least the odor portion of spearmint. 2 very different smells because they're both reacting very differently with the inside of your nose, even though both molecules have the same number, types of atoms, and the same branches. They just happen to be in different positions. Lactic acid. Here's an example. On one side, we've got the one responsible for sore muscles. That's the one on the left. The one on the right is in sour milk. You'll notice the same number and types of atoms, just mirror images of each other. So how do we draw these? First, start by drawing these 4 structures. Pause the videos while you jot them down. Carbon is in the center, and I've labeled their branches A, B, D, and E just to mean random stuff on the sides. They're nothing specific, but take a moment and jot those down. Pay attention to the dots, dotted lines, and to the more bolded lines. Once you've got them jotted down, let's look at them. If I'm going to draw an enantiomer, I need to show which branches are sticking forward and which ones are sticking backwards in a 3-dimensional way. Those solid wedges show that on the left, B and D are coming out of the plane of the paper, while A and E are going into the plane of the paper. The mirror image of that is on the right, where D and B are coming out of the plane of the paper, C is on the plane of the paper, and A and E would dip back behind the paper a little bit. These are now mirror images of each other, and by using those solid wedges and the dashed lines, I've indicated kind of with a foreshortening technique from art class. Now, some chemists don't prefer those. Some chemists just have come to the agreement that if they're going to draw a pair of compounds, it's understood that the vertical goes in and the horizontal comes out. This is a little tougher to keep track of. You want to be very careful with it. Well, at least with the wedges and the dashes, we catch those visually very quickly. Enantiomers have 1 chiral carbon, so they have 1 mirror image, but there are a lot of carbon compounds that have more than 1. If we have multiple chiral compounds, we end up with multiple mirror images. So how many? Well, if something has 2 chiral carbons, each one of those carbons can have a mirror image, so there's 4 possible molecules. What we get out of this is kind of a formula of 2 to the n, where n is the number of chiral carbons. So if I had 4 chiral carbons, I would have 2 to the 4th possible enantiomers. Go ahead and pause it while you jot that down. Let me show you visually what we're up to. Here's a set of structures. Pause the video and draw these. Yes, I know they take a little bit of time. You're tough, you can handle it. In these structures, we can see that A and B are mirror images of each other. They happen to be 2 deoxyribose as part of your DNA. The 2 carbons that are at the intersections are each chiral. For example, right here, this carbon if we count the branches off of that carbon, has 4 different branches. That makes it chiral. This carbon here is also chiral. It has 4 different branches. So this mirror image of it is the enantiomer. However, coming down here to the bottom, looking at C and D, you'll notice my arrangement of the hydrogen and the hydroxy branches are different. But once again, I've got a chiral compound here and here. Its mirror image, its enantiomer, is to the right. So C and D are enantiomers of each other. Take a moment and jot that down. So if A and B are enantiomers, how do A and D relate to each other? Or A and C? Well, they all fall into a category of stereoisomers. Stereoisomers that are not mirror images are diastereomers. What? Stay calm. These are the same 4 examples. A and B, we said were mirror images of each other. Look at A and D. In A and D, I've only reversed the top carbon, chiral carbon, this one. The bottom matches still. So these two have been reversed, whereas the lower chiral carbon in each one has stayed the same. So that makes those 2 diastereomers. A and C are diastereomers of each other, A and D, B and C, and B and D. So here's what I'd like you to try out. I'd like you to add to yesterday's work problems from Chapter 7, 5, 7, and 9. You have to hunt to find the page numbers for that. But all of these have you looking for those chiral carbon compounds that we did in yesterday's assignment. I hope it goes well, and write down your questions. Don't surrender on these. Give it a shot, and let's make corrections rather than backpedaling.